Thank you everyone for joining me this evening. My name is Aaron Pitcher, and I'm here today to give you a talk on 500 kilometers of wireless tethering, an introduction to satellite communication. This is a live lecture series brought to you by Space from Your Place and part of McMaster NEUDOSE. To begin, just to go over some live lecture etiquette. During the presentation, we just ask that you please keep your microphones muted. They should already be muted. If you have any questions, feel free to ask them in the chat. I will attempt to answer most of them come the end of the presentation. And we also just ask to keep the chat discussion with it to a minimum so that we can find those questions when we get to the end. So 500 kilometers wireless tethering, an introduction to satellite communication. So an outline for discussion tonight, we're going to go over a little bit about me. What is a satellite? What are satellite orbits? More importantly, the reason why we're here is what is a satellite communication? We're going to talk a bit about the electromagnetic spectrum, the frequency bands and their allocation. We'll talk specifically about some of the hardware that's used to actually achieve this and how we actually achieve information being sent. And then we'll kind of go over, how do we actually make sure that our communication link will work when we actually send our satellite into space and some of the challenges that we will be facing. So those that aren't aware of McMaster NEUDOSE, shown here is a photo from our high altitude platform back in 2008, where we have our payload here, which is a first edition of our satellite. That will hopefully, with some more modifications, will actually be flying from the ISS and in orbit. So a bit about me. I am the team lead of communications for McMaster NEUDOSE. I lead a team of about 11 undergraduates and graduate students on the design of our onboard radios and antennas on board the satellite, as well as the design of our ground station, which is actually being built at McMaster University. I am a PhD student at McMaster. I received my bachelor's of electrical engineering in 2016 from McMaster, as well as my master's of applied science in 2019. My research interests are those relating to RF and microwave engineering, specifically design of radars and communication systems. Now, you might be thinking microwave is another thing that we actually, cook our popcorn with. Not that microwave. I'll get to it later on, but the microwave is actually, in this context, a part of the electromagnetic spectrum. So, what is a satellite? So, starting from an astronomical term, it is a celestial body orbiting the Earth and around the planet, or around a planet. So this means that basically the moon is a satellite to Earth. And that terminology was actually adopted by the aerospace community. And their terminology for what an actual satellite is for an aerospace is an artificial body placed into orbit around Earth, the moon, or another planet in order to collect information or for communication. So examples of these could be shown here on the right, where we have the SPEC 1 or the Hubble Space Telescope, and more recently missions where we have the radar sat from the Canadian Space Agency that's mapping the Canadian's geographic surface, as well as the Parker Solar Probe, which is attempting to get us the closest man-made object to the sun. And then there's Starlink, which is created by SpaceX. So shown here is all of the objects currently in space. I captured this last night from a website called stuffin.space. And shown here is basically every single one of these dots is either a satellite, so that are the red dots. The blue dots are leftover rocket parts or rocket bodies. And then the gray dots is any sort of debris. As you can see, it's relatively cluttered in our atmosphere. So that's a lot of stuff. So what does all this stuff really do? Well, a lot of it provides us access to telephone, television, radio, internet access, and most importantly, global communication, connecting the world on a global scale. These satellites also have functions for global positioning systems and navigation. You use them day to day whenever you use Google Maps. Military functions, as well as scientific functions such as observation of both Earth and the stars. Specifically for Earth, we're talking at mapping the actual Earth's surface, monitoring the climate, weather and environmental effects of the Earth all year round. When we're looking at the actual stars, we're mapping galaxies, discovering new stars, new planets, black holes, studying the creation of universe. And the main aspect of a lot of these scientific payloads is in order to push the boundaries of human knowledge and for space exploration. So I'm going to talk a little bit about orbits. As you saw in a couple slides back, everything was very densely packed. So how do these satellites actually orbit our Earth? Well, there's three main types of orbits. And then there's multiple regimes that we've kind of classified at certain distances from Earth. So orbits that we're talking about, we have the polar orbit. So that orbits from our North Pole to our South Pole. We have the equatorial orbit, and that orbits along the equator. And we have an inclined orbit, which orbits somewhere in between the equatorial orbit and the polar orbit. Now, each of these orbits have different regimes that they can orbit within. And so shown on the right here is basically the different distances from Earth and our classification for each of those regimes. So we start with the low Earth orbit. So this is anywhere from the altitude range of 160 kilometers to 2,000 kilometers. We then go into the medium Earth orbit, which is anywhere from the range 2,000 to 35,786 kilometers. And we have a relatively interesting orbit called the geosynchronous orbit, and that is specifically at 35,876 kilometers. And what's special about this orbit is its orbit's period is exactly 24 hours. So within this orbit, that's where we have our global positioning systems and our communication systems for cellular wireless communication. And the nice thing about it is that when they're put into orbit at this altitude, they will maintain on top of the same position in Earth. And that's due to the fact that it has the exact same orbit period. Now, most of the satellites actually live within the low Earth orbit. And that's exactly where the ISS is. And this is actually where the McMaster NEUDOSE mission is going to be. So moving on to the real reason why I'm giving you this discussion today. And that is, what is satellite communication? How do we do it? And why is it important? So it allows for the control and reeling of information between two devices. So primarily we're looking at the ground station, which is a station located on Earth, and the satellite, which is orbiting the Earth. And so the goal is just to establish an audio or a digital communication channel by using electromagnetic waves. And so here there's two common terminologies that we like to use. There is uplink and there is downlink. So uplink is how we actually send telecommand. We send our commands from the ground to our satellite. And downlink is how we actually receive our telemetry, our scientific data, anything that satellite's actually doing that we actually wish to recover here back on Earth. And that's basically sending our data from the satellite to our ground station. So in essence, this is what is happening. So we are transmitting some signals up from our ground station, and we are receiving and communicating back to our ground station from our satellite. So how do we actually do all these communications? Well, we use a part of the electromagnetic spectrum. So the electromagnetic spectrum is a set of all the possible frequencies within the known universe. And so this covers everything from gamma rays to X-rays to ultraviolet rays to visible light, as well as infrared, and most importantly, microwave and radio waves. And so for our actual communication, this is actually what we use for communicating with the satellite. And so the radio waves start typically at about 3 kilohertz to 3,000 megahertz. And microwaves, which is what I was talking about earlier, is actually a region within the electromagnetic spectrum. And that goes from about 300 megahertz to 30 gigahertz. And so shown on the right here is the full electromagnetic spectrum, but we can actually see what parts of it actually reach the Earth. And I'll get into a little bit later on as to why certain signals don't quite reach the Earth, but we are highly interested in this radio region, which covers the radio and microwave signals. So the nature of our electromagnetic spectrum. This is something that some people may not typically have ever really thought about, but it is actually a natural resource. It is more importantly an national and an international resource, such that it is shared across borders, it is shared around the world. However, it is finite but renewable. So it's finite in that there's only so much of the spectrum that we can actually physically use. And it is renewable because it's not always being used, right? Take, for instance, your cell phones. They don't continuously stream data. They will buffer and send packets here and there. But it is renewable because they aren't constantly being used and it's being replenished every second. However, like air and water, it can be polluted. So through interference and noise, people can actually interfere with your signals, stuff like that. So it can be polluted and it become very noisy. It's also scarce. And because it's scarce, it creates an economic value. So this requires the need for spectrum management at both the national and international level. So in terms of actually licensing ground stations and licensing our satellites, we actually have to go to the Canadian government. We need to go to the International Telecommunications Union. And these will grant us the licenses based on our needs. So within the microwave and radio wave spectrum, we're broken up into many different frequency bands. And so what's shown here is a table of all the frequency bands that have been defined by the International Telecommunications Union and their frequencies at which we can classify each one as. And so the designation is what you may have possibly heard before, more specifically things like high frequency, very high frequency, ultra high frequencies, and that relates to a certain specific frequency band as well as a wavelength. And so each of these bands have their own services that covers anything from like submarine communication, navigation, sonar, atomic clocks, telecommunication, audio, radio, amateur radio, sorry, and everything that we use basically on a day-to-day basis. And what we're primarily concerned about for satellite communication is this small bit of the band right there. So we went from the giant electromagnetic spectrum down to our, microwave and radio waves, and now we're going down even smaller into the band that we can actually physically use for satellite communication. And this ranges anywhere from 30 megahertz to about 50 gigahertz. And I'll explain in a little bit as to why we stop at 30 megahertz and why we stop at about 50 gigahertz. So how do we actually go about assigning our frequencies and our allocations? We know that the frequency spectrum is a very hot commodity. Our cell phone providers pay big bucks for their frequency bands. Everyone has a piece of the pie, basically, from everything from like your policing radios to aircraft radios to the amateur community, much like our team. And so the challenge here is that satellite services are actually shared with terrestrial surfaces, so Earth surfaces here on Earth, and that influences our interference and our noise. And that's why we have to have specifically allocated frequencies for satellite services. And this allocation is achieved on a national and international level. And it's shared frequencies with other satellites that are in orbit. And so if you consider when they send a bunch of satellites up, you know, making sure that everyone has their, again, piece of the pie, but is not going to interfere with each other is very, very important. And therefore we need essentially careful coordination in launch vehicles and launch providers to make sure that we have our frequencies aligned on an international scale. So how do we actually propagate these waves? Well, it's actually, it can be defined as an electromagnetic wave, or sorry, as an electric field and a magnetic field working together. In this case, they are oscillating together to produce an electromagnetic wave that can move through any sort of medium or space at different frequencies. So a very common example of this is the audible sounds. These range from about 20 hertz to 20 kilohertz, and what allows us to communicate much like I'm talking to you right now. The only difference is because we're higher on the frequency spectrum, or the electromagnetic spectrum, these are actually traveling at the speed of light, which is approximately 3 times 10 to the 8 meters per second. If you really wish to be more pedantic, it's the number that I've shown here highlighted. So with these propagating waves, we can actually do some really interesting things to leverage our abilities to communicate between our satellite and our ground station. And we can do a certain thing with relation to its polarization. So depending on whether the electric field and magnetic fields have components in both the XY plane, or shown here, the vertical and horizontal planes, you can create different types of polarizations. And certain polarizations can communicate with each other with known losses, or certain polarizations actually can't communicate with each other, which therefore leverages the ability to use the same frequencies, but have differently polarized waves so that you can actually still communicate. And so shown on the left, top left here is a horizontally polarized wave. So that is a wave that has an electric field that's just oscillating in the horizontal plane. On the right, top right, we have a vertical polarization, just oscillating in the vertical polarization. You can actually get an angled polarization, or in this case, this one is showing a 45 degrees. And if you have multiple components, both in the horizontal and vertical axis, you can actually get what's called a circular polarized wave, in which it actually rotates around a circle. And so using these polarizations, we can actually achieve communication and no minimum losses based on how the actual electromagnetic waves are traveling through the air. So I'll promise this is the one and only equation in this whole entire slide set. And it's a pretty important one for the electromagnetic waves. And that is basically the relationship between frequency and wavelength. So frequency, everyone understands hopefully what frequency is. It's just the rate at which something occurs or is repeated over a particular period of time. And in this case, it's defined as the units hertz, or 1 over a second. And wavelength is actually the distance between identical points of the adjacent cycles of a waveform signal propagating through space. So what does that actually mean? Well, what it is the distance traveled over that frequency, over one period of that frequency. And so shown here is basically the relationship of that, which takes into account the speed of light, which again is meters per second. Our units that we wish to get for frequency is 1 over a second, and our wavelength is typically defined in an actual distance, say meters. And so it's a very simple calculation where frequency is equal to the speed of light divided by our wavelength, lambda. And so shown on the bottom here are those electric and magnetic fields. And we're showing here the wavelength is the distance between this node here and this node here as it's being repeated repetitively. So how do we actually go about creating these signals? And that's probably the real meat and gravy, and it's the real challenging part behind electromagnetic radiation. So there's tons and tons of components that you'd ever actually require. However, I'm just going to highlight some of the key aspect ones that we need here in order to make any sort of radio communication link. And so we'll need a couple radios. We'll require some filters, both low pass and high pass filters. And then we'll require some amplifiers, some antennas, mixers, and local oscillators. So just a definition of what a low pass filter and what a band pass filter is. A low pass filter will allow signals below a certain frequency to pass through and attenuate signals that are above a certain frequency. And by attenuating, I mean reduce the signal ideally to 0 so that no signals actually pass through. A band pass filter allows only a certain band of the frequency spectrum, which allows basically us to reduce the noise, reduce the interference from other people that are using the electromagnetic spectrum, while still being able to receive our signals. And so on the right side here, there is basically a block diagram of a receiver, of a transmitter and a receiver, which incorporates all of the components that I've listed out here on the left, where the transmitter would pass through the radio, a low pass filter, some mixing and up conversion to a higher frequency, and then some additional amplification and filtering so before it gets radiated from the antenna. So this would be either located on the satellite and or located on the ground station, depending on which way you're trying to communicate. And then on reception, the signal would come from the transmitting antenna to the receiving antenna, and again go through a similar process before it gets to the actual radio, so we can actually recover whatever data and information that we are actually sending. So this is just some pictures of some satellite hardware specifically for CubeSats. These boards are the size of 10 centimeters by 10 centimeters. So the top here shows some of the radio communications boards that are commercially available, whereas the bottom are some of the antennas that are actually available. So on the left-hand side here, this is an antenna, which is either like a dipole antenna, or can even be a quadritage antenna, which basically will produce the circular electromagnetic waves. So in part of the actual NEUDOSE mission, this is our communications radio here that our team's been developing for about 5 years now. And shown on the left is actually, I think, the first time we've ever actually achieved communication from our satellite shown there, and you'll see blips on the actual computer. And so our team's, this is, that was, at that time was in 2018. Our team has since designed a new revision of our board, which is shown here, which encapsulates all of the components that are actually required to do full communication. And so much of the stuff that I showed in that previous block diagram is in this high frequency section here. And everything else is actually just to support that part of the functionality. So shown on the left is the top side, shown on the right is the bottom side. And inside this high frequency section, we have chips like the radio shown here. We have some filters, which is this giant block. We have some amplifiers. So this is part of the receive chain. And on the transmit side, we will have the radio shown here, and another filter, some amplification, and we'll go out this connector to our antennas, which will actually transmit and radiate our signals back to Earth. In terms of some ground station hardware, typically they look a lot like any of these photos shown here. The top left two are ground stations for low Earth orbit. So we can see we've got some antennas here, and they basically position in 360 degrees along the azimuth. So that is along the Earth's surface, and elevation, they'll go 180 degrees. So that is basically, they can go full overhead from north to south. These other giant dish antennas, they are typically more used for astronomical purposes or deep space communication or higher frequencies. And so shown on the right here are actually ones that are located in Canada. The top one here is, I believe, from Quebec. It's in Gatineau, and the bottom one is in Saskatchewan. This is a typical actual box of a radio. It's a commercially purchased box that actually takes up a server rack because of how big it actually is. And so what you would do is you would actually connect this radio box to any of these antennas, and that would deal with your communication link on the ground station. In terms of the actual NEUDOSE mission, these are some of the components that we've actually been able to purchase and put together. And so shown on the left here is actually our ground station mobile system that we have. So these mobile system will be used for our high altitude balloons system that Paula was talking about yesterday. And all of the components that we require to actually do that. And so we've got our radios here, an actual server that's going to run all of our data processing and managing of the radio, as well as the actual antennas and positions themselves. Specifically, this is a UHF or 435 megahertz antenna. Depending on what frequencies you're using, the antennas will look differently. But this is just one case example that we're using for our mission. So I've talked about the hardware. I've talked about orbits and how we actually communicate, but how do we actually like send the real data? The stuff that we really care about, you know, is our satellite still alive? And do we need to do anything to tell it to reset or troubleshoot because something isn't operating nominally? And so that brings us to how we actually send our information. So there's two typical modulations that we normally use. And originally, all of these electronics and everything was done in an analog fashion. So it's like real world signals. And there are three common things that we can actually do to that signal. So those sinusoids that I showed, the electromagnetic waves, what we can actually do to it is we can affect its amplitude, its frequency, and its phase. So amplitude is the strength of the signal. Frequency is at what rate it is running at. And phase is how the periodics of it are related to one another. And so what you'll most likely know is that we have AM and FM radio. And that's what they typically use because they're mixing audio signals, which are real world signals, with some up conversion carriers to modulate our data using analog signals. But when the digital world started to evolve, we had to come up with new ways of modulating, because now instead of modulating a audio waveform, we're modulating zeros and ones. And so they basically took the same idea of amplitude, phase, and frequency and implemented it into a digital modulation fashion. And so the three most common that is used is ASK, FSK, and PSK, which stand for amplitude shift keying, frequency shift keying, and phase shift keying. So you might be thinking, well, what does all this actually do? So that is the picture on the right of the screen. So we have a stream of zeros and ones. This could be saying, you know, hello, McMaster NEUDOSE, hello world, this is me, whatever we actually wish to send, but is in a binary fashion or in zeros and ones. And what we do is we actually modulate that with a signal. It's called the carrier. And the carrier is typically set to whatever frequency we wish to operate at in the RF or radio and microwave part of the electromagnetic spectrum. And so when we do amplitude shift keying, you'll see here that a 1 has full amplitude, whereas a 0 actually has very, very little amplitude, and will modulate like that. We actually talk about frequency modulation. What we're going to do is we're actually going to change the period or the frequency of the signal such that a 1 would look something similar to this and a 0 would look something similar to this. And then finally, when you actually get to phase shift keying, what you do is at every period, you actually flip, it almost looks like a mirror about the time axis, so that you're flipping the actual phase 180 degrees with respect to the previous bit that you're sending. These are only a very brief amount of signals, or brief, modulation that we can do, and there's absolutely so much more, and they get very complicated very fast. So I'm just going to play here a little clip, basically sounds from the ISS, so you can actually hear what these frequencies and this modulation process looks like. And so what you'll hear is an audio of 2 frequencies buried in with some static noise, and I will now play that. And so what each of those tones after, so you'll hear like some static noise that you typically hear on a radio, and you'll hear like a little section of actual two signals that sound almost like a dial-up connection from when you used to dial up for internet. And what's actually encoded in that is the messages shown here below. And so what you'll see is that you actually are sending this ARISS, which is the call sign of the ISS satellite, and then they'll say the International Space Station. And again, you get the same sort of message. And then someone here from Utah actually transmitted to the ISS, and they repeated it back to them. And so you can see here, they provided some GPS locations, and they say hello from so-and-so, and this is their personal call signs. And this is how we actually go about communicating. And this is one way that is typically done. So the last sort of major question is, how do we ensure all of this all works together before we send everything to space? Once things are in space, obviously we can't just, go up to it and troubleshoot it. It's a very challenging aspect of, how to troubleshoot something when it's orbiting some 5,000 kilometers above you. And the key aspect here is that, yes, it can work. It's going to take a great amount of work and a lot of dedication from our team and any team that does anything like this. But there is some things that we can do to ensure that it actually does work. And so this brings about the typical questions as often is, are we in budget? And what this means is, are we within our link budget, which is a calculation that's used to account for all the gains and losses in our telecommunication system. And so this is everything from when we actually transmit our signal to when we receive it, along with everything that passes through it. So shown here in the figure is, the signal strength that we are expecting to see, and the path that the signal has took. So as we're orbiting above Earth, we've generated some signal that has some signal strength, and we may get some additional gain here from either like an amplifier or through the antenna. And then as it gets traveled through the air, through the atmosphere, we see a drastic drop in the signal strength. And then once we get back to down on the Earth, we'll see, you know, maybe a little bit more gain because the antenna has a gain, or we have some more amplifiers here, and then you'll reach some nominal received signal level. Now, the main challenge with link budget, or main challenge with actually all satellite communication, is this middle section where we see giant path losses. Typically, you see anywhere on the orders of 140 to 160 dB. That is decibels. So in a linear fashion, or what way you can describe it, is you see a reduction in the signal strength by 10 to the 14 or 10 to the 16 times the signal strength. And so that brings about some real challenges in how we actually communicate with our satellites. So besides from just the typical electronic losses and connections that we already have, there are other additional challenges that we face. For starters, satellites are limited on power. We already start with relatively weak signals. On top of that, depending on how accurate you are pointing your ground station at the position in the sky as to where you think your satellite is, you'll have losses. Going back to polarization, we can have a polarization mismatch, which is basically the polarizations between the two communication systems actually don't fully mirror each other, and therefore we have additional signal losses again. And then finally, the last two that we actually see are what's called atmospheric absorption, which produces even more signal losses, and ionosphere absorption and scintillation, which gives us, again, even more signal losses. And so atmospheric absorption, we'll go back to this picture that we talked about much of the beginning of our presentation. And this shows how our atmosphere will absorb basically everything of the electromagnetic spectrum. So the signals that actually get all the way down to Earth, or that of the optical region, as well as the radio region. And the reason that we can't actually go above, say, 50 gigahertz is due to the electromagnetic waves interacting with water and oxygen molecules. And so the graph on the right here basically shows the amount of attenuation that we see based on its frequency. So as our frequency increases, our losses due to absorption by water and absorption by oxygen increase. And the two main aspects that we can't typically use is around 20 gigahertz, and then from 50 gigahertz and beyond. And that's just due to the physical properties of the molecules, as well as the electromagnetic waves and their traveling. And when we look at actually ionosphere losses, or absorption, sorry, and scintillation, you may hopefully capture, or you're here for your, the presentation yesterday, where Paula went through all the different layers of our atmosphere. And there's a couple additional things. We have what's called the ionosphere. And at certain layers, this is where the electron density of all the molecules are the highest. And depending on the frequency that you're actually transmitting at, the signals actually won't fully travel all the way through. So the diagram on the right here basically shows that some signals will go through, and they will actually will have small fluctuations that cause basically refraction and diffraction, or scattering of the electromagnetic waves, which basically would not allow the signals to pass through, where some frequencies will actually penetrate through these layers. And these are typically signals above 30 megahertz. And so the interesting thing is that we can use this ionosphere to our advantage, but but it's also a challenge to us. People use the ionosphere for at 30 megahertz to communicate around the other side of the world, using something called skipping. and that's where we will actually transmit our signals and actually skip it off the ionosphere. But in terms of actual satellite communication, it's a hindrance for us to go anything lower in frequency because our signals actually just won't penetrate the ionosphere. So lastly, just some fun facts. These are some just extreme facts from NASA. So I'm just gonna read it here. A signal that spacecraft uses to contact Earth typically has no more power than that of a refrigerator light bulb. And by the time it actually reaches Earth, it is 1/1,000,000,000 of 1/1,000,000,000 of 1 watt. So if you think of your old incandescent light bulbs, they were like 60 watts to 100 watts. We'd be lucky to use a couple watts on the satellite, and we're going to get 1/1,000,000,000 of a 1,000,000,000th of that. To detect these tiny signals from space, the Deep Space Network, developed by NASA, uses some antenna dishes that are up to about 70 meters in size, and that's almost the size of an actual football field. And another final interesting fact is the Voyager 1 and 2 are technically still operational today. And Voyager 1 is actually the first interstellar spacecraft. And so shown here is a time lapse of the mission that was launched in 1977, upwards to about an hour ago. And we can see that the satellite is currently 22 billion kilometers away from Earth currently, which is remarkable considering its 42-year life cycle. And to actually communicate with those signals, that is why they need these deep space networks, and why you see 1/1,000,000,000 of 1/1,000,000,000 of the actual total power transmitted. How to get involved? Check out McMaster NEUDOSE on social. We've got Instagram, Twitter, Facebook. Shoot us an email, check out our website. Our team is currently hiring for many positions. I would go and check out McMasterNeudose.ca/recruitment. We're constantly looking for anyone with firmware and software experience, hardware and electronics experience, mechanical and design experience. And if anyone that's actually interested in actual radio and electromagnetic waves, you can always get involved with your local amateur radio club. The guys in Hamilton have been very helpful in our licensing process and supporting us. And this is a community of well-versed and well-educated people in the radar or radio community. Thank you very much. I will now take any questions, if there is any. So what are the uses for skipping radio signals? So the uses of skipping radio signals is what would allow people to communicate. Typically it was used something back before we had all of the global communication that we have today. And so people would actually hold, or even the amateur community holds competitions for, longest communication. So what they would actually do is they would try and set up in a position where they could have the best chance of skipping waves off the ionosphere to try and connect from, let's say, Hamilton to Australia, basically the other side of the world. And you can actually skip radio waves off of the ionosphere, and hopefully sometimes you can actually trap them occasionally in between the two and communicate. Hopefully that answers your question there. So a question from Andre is, why did we decide to use VHF and UHF radios for communicating with the NEUDOSE instead of higher frequency? So part of the reason for that is due to the atmospheric absorption. Anything, once you start getting above, say, 10 gigahertz, you require a lot more power, and the amount of power that you put in, you don't necessarily get the full power back when you receive it on the other side. The other aspect is VHF and UHF have been well used for missions in the past and have well-documented designs out there. And when you go higher in frequency, you often require what's called an altitude determination and control system so that you can actually point your antenna towards Earth. And the McMaster NEUDOSE mission actually doesn't have that system. And so we can leverage using UHF and VHF along with dipole antennas, which radiate in an omnidirectional manner to basically communicate with our satellite with actually not requiring the ADCS system and higher frequencies. The benefit with going with higher frequencies is that you can achieve more data transmission. So on UHF and VHF, we're limited to kilobytes a second. If you start going to, let's say, 2.4 gigahertz, like your Wi-Fi, and higher frequencies, your bandwidths become upwards to megabits a second. And so you can actually get more data. But as we looked at it for our mission, the amount of data that we wish to collect, we only, the UHF and VHF meets our requirements and is the most safe and robust system that we have come up with to achieve our mission, Hopefully that answered that question. Cool. Well, in that case, I will thank everyone for joining me this evening. I hope everyone is doing well and staying safe, and happy Easter to you all. Thank you and have a great night.